Welcome back another class of electronic device. So let's see what the resistance and drift and resistance. In last class we have seen drift in detail. We have derived a current density equation of charge carriers in the electric field, that is drift. And what is the resistance? We'll see the resistance. So the resistance equation we know already. Resistance is equal to rho length divided by area. Resistance is proportional to length of the semiconductor. Resistance is inversely proportional to area of cross section, and this is resistivity. Okay, Roy's resistivity. That I can see the area here. This is the length. Okay, this is width. And this is a thickness basically. So area is equal to W into T, because this is the cross sectional area. Okay, and the conductivity 1 by rho. Rho is equal to 1 by sigma. This is a resistivity, this is a conductivity. Resistivity unit is ohm, conductivity unit is mho. Okay. So here this equation remains same. Resistance equation of drift charge carriers inside a semiconductor is still same, no doubt. And what exactly I want to tell you, it is something like this. So here this is a x-axis, this is origin, this is x is equal to L, because length of the semiconductor is L, this is width represented as W, and this thickness is T. So look at this, the electron motion always opposite to the electric field. One source is connected here, plus minus. Okay, so electron will flow in this direction. So electron will flow and electron will enter at the point x is equal to L, and electrons leave this semiconductor at x is equal to 0. So basically the electron, it's very easy to visualize the electron flow through this path. Electron is flowing. Okay. So electron will enter into the semiconductor at the x is equal to L, and that electron will leave the semiconductor at x is equal to 0, no doubt. So the concentration of electron in the semiconductor, if it is N, that remains same. Because electron is pumped by the source, it's circulating. And what about the holes? We know that electron is moving opposite the direction of electric field, so that the current is basically opposite the direction of electron flow. So electron motion is this side, so that current is like this. Then we know that holes move opposite direction of electron. If I compared with the current direction, the holes moving direction and the current flow direction, both are in same way. The electric field also in the same direction of holes. The current is also in same direction of electric field. So holes, it's very difficult to visualize, to move the holes in this path. Electron will flow this way. What about the holes? So holes actually move this direction, and at this point, at the x is equal to L, at the point x is equal to L, what will happen? The hole is going to recombine with the electron which is supplied by the source. So holes is disappear at this point, and the holes will generate at this. So what I can say blindly, the current flow in the external circuit is because of the electron, and current flow inside this semiconductor is because holes. So you can see hole is moving from this side to there. Basically electron actually jumping from one position to other position of hole and reaching this side. So you can see the hole is moving this side and recombine with the electrons here. Similar way, holes is generating at this point. Okay, that is what written here. If we consider that current is carried the external circuit by electrons, every electron leaving the left end x is equal to 0 of the bar in the figure, there is a corresponding electron entering at x is equal to L, so that the electron concentration in the bar remain constant here. As a whole reaches the ohmic contact at the x is equal to L. Okay, what is ohmic contact? Nothing but if a semiconductor, we need a lead, right? External lead to connect the external source. So this contact between metal and semiconductor is known as ohmic contact. So ohmic contact at the x is equal to recombine with the electron, which must be supplied through the external circuit. As this hole disappears, the corresponding hole must be appear at the x0. So holes and electrons are moving inside. Now the picture is more clear to you about holes and electrons, right? Externally it is very easy to visualize the hole is moving, but what happened inside the semiconductor, both holes are there and electrons are there, which will move opposite direction, and but the charge is different. Okay, electron moves opposite the direction of electric field, but current and electric field and holes are in same direction of motion. The resistance is equal to rho L by Wt, where Wt is the area of cross section and rho is the resistivity, and 1 by rho is nothing but conductivity. If rho is, the unit of rho is ohm, resistivity, and unit of conductivity is mho. OHM m mho. Okay, thank you. That's about the retained resistance.